Welcome back, y'all. We are in the LANA algorithm. We're running through a complete circuit analysis to break down all circuit variables as linear algebraic equations. We're looking at example 2. In this video, we take a look at our quick reference guide to the linear algebraic nodal analysis, LANA. We are now in step 4 to create all circuit vectors. Instead of just staying with the quick reference guide, we're going to go to step-by-step analysis to figure out what we're supposed to do here. Step 4 is dedicated to creating all circuit vectors. The vectors are going to store circuit variables. In this specific circuit that we started with, we have 12 circuit elements. Each circuit element we assign 2 variables. One variable is the voltage drop across each element. So if I attach the negative lead of a multimeter to one side, the positive lead to the other side, I can get a measurement, which is the voltage drop across it. Same thing with an ammeter. If I do it in series, I can get the current running through it. So each element has current running through, voltage drop across. There are 12 elements. That's 24 circuit variables. In addition to that, we're going to have something that we call the node voltage potentials at each node, which is if I connect the negative lead to one node in my circuit and then move the positive lead through the other nodes, I can get measurements for all of those node reference potentials with relation to the actual ground node that I choose. So that's 24 plus 7, that's 31 circuit variables. Instead of storing each of those as an individual scalar, we're going to store those in vector form to make our life a lot easier. This comes into a lot of play as we get further down on the list of steps in our algorithm. Using our step-by-step guide to the LANA algorithm, we see that step 4, create all circuit vectors, actually has a number of sub-steps. Remember, in step 1 of this video, we erased the circuit bodies to identify the circuit nodes. What we're now going to do is say, remember that if we attach the negative lead of my multimeter, the black lead of my multimeter, to one of the nodes, and then I pass the red lead over to the other nodes, I'm going to get measurements of the voltage potentials at each node with respect to that grounded node, the node that has the black lead attached. Thus, we would expect, if we're going to capture that data in variables, we expect 1, 2, 3, 4, 5, 6, 7 different measurements, and we create a vector U sub G, the vector of voltage potentials at each node, including ground node. We haven't grounded the circuit. That's why when the G is there, ground is included. Here, U1, U2, U3, U4, U5, U6, U7, that's the exact process we were just talking about. When I pass that voltmeter along those nodes, get the reference potential at each node, store those in vector form. In this case, this is a 7 by 1 because it's the number of nodes in the circuit stored in a single column. The next sub-step to create circuit vectors is to define the voltage drop variables across each element. To do this, we actually need to define the reference directions. And remember, in our reference directions, we're going to use the digraph model and say that the voltage drop happens in the direction of our edge from positive to negative. So let's imagine for a moment that I wanted to define the voltage drop across resistor 1. I know that resistor 1, it corresponds to edge 1. That goes from 1 to 7. So I go from positive to negative, and now I have a single voltage drop across resistor 1. Same thing, resistor 2. I'm going to go from positive to negative. This is going to be the voltage drop across resistor 2. And in fact, using my digraph model, I can assign reference directions and variables for the voltage drops across all 12 elements and store that information in a single vector, which we call the voltage drop vector. In the way that we did this, we're going to assign the numbers, the index for each element of that vector based on the edge number that it corresponds to. So edge 1 corresponds to resistor 1. That voltage drop is V sub 1. And we actually have a polarity. The moment that we've determined our directed graph model, the polarity of each of these measurements is actually encoded because remember, the edge always goes from positive to negative. Because we've grouped edges and enumerated them within element type, we can automatically partition this voltage drop vector within each element type. So V sub R is a sub vector that represents the voltage drops across all the resistors and only the resistors. V sub V is the voltage drops across each of the voltage sources, and V sub I is the voltage drop only across the current sources. We stack those on top of each other to have the entire voltage drop measurement, and then encoded within this is this information. Notice this enumeration and that subblock partition is the same style of enumeration and subblocking that we did in our incidence matrix. The last required step in step 4 to define all the circuit variables is actually to define the current running through each element. And we already know that the current running through each element is actually pegged, is connected to the way that we define the reference directions for the voltage drops, which is directly connected to the way that we oriented those edges. In other words, we're going to say that for each element, not only does it have a voltage across, but it has a current running through, and we're going to store those currents in a vector with reference to the directions defined by the digraph model of our circuit. When we do that for all 12 elements, we get the following vector. This vector is a 12 by 1, or another way to say that, it's the number of elements by 1, because each element has a single current running through it. This leads us to 31, or another way to say that is number of nodes plus number of edges plus another number of edges, different circuit variables required to describe the entirety of our circuit together. One of the pieces of magic of this is we're actually going to simplify, we're going to kind of translate many of these variables to a subset of these, which means we turn a 31 variable system into something, in this case, like a 4 variable system. So translate 31 variables, get them down into 4 variables, and then use matrix structures to solve for those 4 unknown variables and completely determine the entirety of how the system functions. I should mention that there's what I like to call an optional part of step 4, the last part of determining the circuit variables, which is to redraw the circuit with all of the variables labeled. And you'll see that's what's happened here. I've redrawn the entire circuit with all the node voltage potentials labeled. I've also, for each element, assigned a current direction and a voltage drop and done the enumeration under the proper scheme talked about in step 2. When I do this, I actually note immediately that the voltage drop variables across the voltage sources are not unknown. We actually know those values because by definition in this circuit, the voltage sources provide a known voltage drop across the leads. Also, the currents running through the current sources are not unknown. These values, the variables for the currents running through these 2 sources right here, are known to start with. In fact, the 2 students that designed those little circuit elements spent many, many months of life, along with the kind of master engineer that helped us with this project, making sure that we could claim that these values are known. In terms of what that means mathematically is when we stack this vector, these 2 elements are actually not unknown, they're known. So the V9 and V10, the voltage drop across voltage source 1 and the voltage drop across voltage source 2, V9 and V10. I sometimes like to say VV1 because that's the voltage drop across voltage source 1. VV2 is the voltage drop across voltage source 2. Those values are known and they're actually given in the circuit schematic. What's the voltage drop across voltage source 1? It's 5 volts. What's the voltage drop across voltage source 2? It's 5 volts. We can measure that in the corresponding circuit. Those are DC sources. I'm good. Which means a subsection of these are known values, not unknown variables. The same thing is true for the currents running through the current sources. What is the current running through current source 1? Well, in the schematic, I see that it should be 2.5 milliamps. Same thing for the current source 2 should be 2.5 milliamps, which means this subblock of my vector is not an unknown set of variables, but instead they're a known set of variables. I know how much current is running through it because it's designed into that particular circuit element. I should note that the current running through current source 1, it should be called I11 in terms of the enumeration, but sometimes I like to call that I sub I1, current running through current source 1. I sub I2, current running through current source 2. With that, we have completely defined all circuit variables, stored them in a very structural way in an organized method using vectors. Those came from taking the original circuit, labeling the nodes, labeling reference direction for both voltage drop across and current running through, as well as the node potentials associated with that. When we redrew that entire circuit, the graphical representations of the reference directions are stored in our redrawing, and implicitly, the moment that we define our digraph in step 2, we get all of this information for free. In the next set of videos, we're going to see how we can leverage this information as well as matrix multiplication and the incidence matrix to discuss Kirchhoff's voltage laws, Kirchhoff's current laws, and Ohm's laws. This is what I was talking about using linear algebra. In the standard approach to this in circuit theory classes, they do it in all scalars, which is cool. But I would say that's the 1950s and 1960s approach. We have much more powerful technology at this time and age, which is called matrices and computers that are designed to run matrix operations at lightning fast speeds. In the next video, let's go ahead and see how to use matrices to state those fundamental circuit equations. I'll see you there.